This is AP Precalculus notes for topic 3.12, equivalent representations of trigonometric functions. Before we dive in, hopefully you have all of these remembered. If you want to find what is cosecant, it's just 1 divided by sine. Same thing for secant, it's 1 divided by cosine, and tangent has a bunch of things to remember. The main thing being if you have 1 divided by tangent of your function, it's going to be cotangent. There are equivalent ways of writing tangent. For example, tangent is sine divided by cosine. Why is that the case? Because y over x is the same thing as slope, and tangent really talks about the slope of a function. If you take the reciprocal of these and flip these upside down, then sine is on the bottom, cosine is on the top, and you've now discovered cotangent of x yet again. All right, so I want to manipulate sine times secant squared all over cosecant, and I want to try to solve this puzzle, and I want to involve only tangent of x and nothing else, which means I have to somehow turn all of these into a sine over cosine. My strategy is to somehow make sure I have all the sines on the top, cosines on the bottom. If I have like 2 copies of sine on the top and 2 copies of cosine on the bottom, that's okay, because that's just going to turn into cosine squared. So let's go ahead and just use the definition of everything to rewrite. I know that I think I should leave the sine of x on the top because it belongs up there in order to make a tangent. Secant squared, though, I don't know if that belongs up there. Secant squared is the same thing as 1 over, I'm remembering this is cosine reciprocal, so it's cosine on the bottom. And because this one is squared, this one down here should also be squared. So I'll say it's 1 over cosine squared of x. Cosecant of x is this, because the middle letter is s, it's going to be sine. So it's going to be 1 over sine of x. And this is more disgusting than we originally started with, but hopefully this will boil down into something nice. I happen to know that I'm going to leave the top section alone. I guess I don't have to leave the top section alone. I'm going to change this into, I'll say this is really sine of x all over 1 times 1 over cosine squared of x. So this entire thing is being divided by 1 over sine of x. And I didn't have to write it that way, but I like to go slow so that the students can see what's exactly about to happen. So from here, I have something, you can ignore what's on the inside, something divided by a fraction. Whenever you divide by a fraction, it's going to be a keep, change, flip. So I'm going to keep this original expression. I'm going to say I had a sine of x on the top and I had a cosine squared of x on the bottom, so I kept it. I simplified it a little bit. I'm going to change the division into a multiplication, and I'm going to take the reciprocal of this and flip the 1 over sine of x, so it's sine of x over 1. And hey, if I multiply the tops together, I get sine squared of x in the numerator, and the denominator is cosine squared of x. And I happen to remember that that looks very similar to sine of x over cosine of x, except everything has been squared, 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 and that's okay. So this is the same thing as saying tangent squared of x. And notice I have hit the requirements. I only involve tangent of x. There's no sine, there's no cosine, no cosecant, no secant, no anything except for tangent. So give myself the check, and that's the process. Let's try another one. So in this scenario, I have a puzzle where I'm trying to only have secant of x and nothing else. So secant, I'll remind myself, is the same thing as saying 1 over cosine. So really what I'm after, my strategy is make sure I put all the cosines in the bottom and only have cosines. I don't want any sines or anything messing me up. So let's use the definition. Let's say that cosecant, this cosecant right here, because the middle letter is s, that's going to be sine. It's going to be 1 over that sine, and this says times tangent of x. Well, tangent is the same thing as writing, I just happen to remember that tangent is like slope. Slope is y over x. Y is the sine, relation of x. X is everywhere. So it's going to be sine divided by cosine. Cosine always gives me the x coordinate. That's how I know cosine went to the bottom. All right. And then from here, oh, look at this. I can see this sine and that sine are going to cross cancel. So if you're gone, you're gone. This is just going to be 1 over cosine of x. And hey, I happen to know that 1 over cosine of x is the goal that I was trying to get. That is the same thing as secant of x. So this all turns into just secant of x and nothing else. So that one was actually really easy, easier than except for 1, I would say. All right. So there's some really interesting ways of rewriting your trig identities, and this first one is really, really important. If you have to memorize one thing from this lesson, there are a ton of things you have to memorize from this lesson, but the one thing you have to learn is the Pythagorean identity. And I want to set this up so that you really understand what's going on here. So essentially, I want to convert this triangle into trigonometry. So if I say this length right here is x. Well, to find my x coordinate, if I have a unit circle, is you say this x dimension is cosine of theta. So really what I had here is p is really x comma y, right? But x is the same thing as cosine of theta. This distance right here is cosine of theta. And this distance here is sine of theta, because sine of theta gives you the height or the y coordinate. So I'm now I'm swapping these out and saying, okay, this is no longer y, this is sine of theta. And this is no longer x, this is cosine of theta. And whenever I have a right triangle, which I do because of how I've constructed this argument, whenever you have a right triangle, I am allowed to use Pythagorean theorem. Pythagorean theorem states you take a leg, square it, add leg, square it. It should be equal to the hypotenuse when squared. And look at what you've written. You've now written leg squared of x, yeah. And then plus the other leg squared is going to be equal to the hypotenuse squared, and 1 squared is just 1. And this is the Pythagorean identity. There's a ton of other theorems that come from this one theorem. You'll be using this, I would guess, more than any other theorem that you'll have from today, more than any other identity. It's not really a theorem, it's an identity, because these are equivalent expressions. So memorize this one. Cosine squared plus sine squared is equal to 1. You don't have to remember it, that cosine goes first. Technically, down here, they did sine first. So you can say sine squared plus cosine squared is equal to 1 as well. That's not a factorial, by the way. It's just very excited to teach math. So let's use this. And by the way, before I go too much further, a general tip on when to use this. Anytime that you see a cosine squared, anytime you see a sine squared, it probably means there is some sort of trigonometric identity at play there. For example, if you see a cosine squared by itself, move the sine squared to the other side, subtract sine squared on both sides, and you've now isolated a cosine squared that you can substitute back in. We'll see that come a few times a day, so be ready. So one way that you can play with this is you can divide everything. So again, this is the Pythagorean identity that we started with. If I divide everything by cosine squared, and I'm just kind of randomly doing this, I'll randomly do something else next to show that another identity pops out of this. Watch what happens when everything is divided by cosine squared. First of all, cosine squared over cosine squared cancel out, and it turns into 1. And sine squared over cosine squared, we just saw that. That's the same thing as tangent squared. And 1 over cosine squared, well, whenever you do 1 over cosine, that's just secant squared. So you get this new identity, which is tangent squared of theta plus 1 is equal to secant squared. And we've built our toolbox of useful identities. There's another useful identity. Where does this one come from? Well, instead of dividing by cosine squared, let's divide by sine squared. Watch what happens. So if I divide all three of these by sine squared of theta, sine squared of theta, sine squared of theta, watch what happens. Again, now sine squared and sine squared are going to cancel out, leaving behind a 1, still a 1. And cosine squared over sine squared is really, really similar to sine squared over cosine squared, except it's the reciprocal. So what's the reciprocal of tangent squared? It's cotangent of squared. And then finally, 1 over sine squared is just cosecant squared. And you've unlocked yet a third identity, all stemming from the Pythagorean identity. So all of these are kind of equivalent forms of the Pythagorean identity. This is the main one that you have to remember, and then you can get to either one of these by dividing by sine squared or dividing by cosine squared. There's another way of looking at this. Check this out. What if we say, hey, let's just randomly say this length right here is x, which is very common to do. Luckily, we're dealing with a unit circle, which means if I want to find what is this length here, you can just say, hey, cosine of theta gives me x, which we'll be using later. But what is this angle over here? What is this side length over here? To find that side length, you have to use Pythagorean theorem. Again, you can use, because we have a right triangle, so you can say, hey, Pythagorean theorem states, let's go ahead and call this maybe h for height. You can say, I can solve for h. Say h is the one that we want, that's why I circled it. So check this out. I'm gonna do leg squared plus leg squared is equal to hypotenuse squared. And 1 squared is just 1. Now, if I'm trying to solve for this h, watch what happens. If I subtract x squared on both sides, I now have h squared is equal to 1 minus x squared. Not very exciting. And when I take the square root, it becomes even more exciting. So it becomes h is equal to technically plus or minus, but because we're going up, I'm going to restrict the domain and just say, hey, it's the positive. It's just the square root of 1 minus x squared. And now I can rewrite this. Instead of saying this is 1x and h, I'm going to say this is 1x and this length is now 1 minus x squared underneath the square root, like this. When I do this, something interesting happens. Check this out. If I take cosine of my original angle, this angle hasn't changed. If I take cosine of this angle, because it's a unit circle, cosine gives me x. If you want to get rid of cosine, I would take the undoing of cosine is arc cosine. I can say arc cosine of this side, and that means I have to do arc cosine of the other side as well. Arc cosine and cosine cancel each other out, leaving behind just a theta. And arc cosine of x is still arc cosine of x. So you can say, hey, this is one of the two things that is interesting. Point one is theta is cosine, arc cosine of x. And let's check out another one. If I'm trying to find what is this length, well, sine of theta gives you that length. And if I want to get theta by itself, I have to undo sine, and I take arc sine of this side, and therefore arc sine of this other side. These two cancel each other out, and you now have theta is equal to arc sine of the square root of 1 minus x squared. And this is the key point. Check this out. So with 1 and 2, these are both saying theta is a thing, theta is also a different thing, but they're the same theta. I haven't changed this diagram, which means arc cosine of x and arc sine of the square root of 1 minus x squared are the same thing. And that's what we're saying down here. Arc sine of x is the same thing as arc, oh, I guess that's the backwards version. There it goes. Arc cosine of x is the same thing as arc sine of the square root of 1 minus x squared. You could have also switched these two. If you switch these two, you get the entire reverse of that, meaning that arc sine of x is the same thing as arc cosine of the square root of 1 minus x squared. And you have inverse trig identities. And again, you can spell them out two different ways. You can say arc cosine of x, or you can say arc cosine of x. They're the same words. This one is like the symbolic version. This is more spelled out. And you can, it's the same formula, just in reverse, so it's super easy to memorize. And it is yet another two things to have in your toolkit that you do have to have memorized. We'll talk about how to memorize these in a second. All right, so let's try to use some skills that we've seen. Okay, so we want everything in terms of only cosine. That's the puzzle. So if I want everything in terms of cosine and no other trig functions, if I see a cosine, put it to the top, everything else, let's just rewrite. So tangent, I know I can rewrite u. I can say, okay, if I originally had tangent of x, all of this divided by cosecant of x, I happen to know that tangent of x is really it's y over x, so y is sine of x over cosine of x. And then cosecant of x is the same thing as 1 over, middle letter S, 1 over sine of x. Okay, again, I have a fraction within a fraction. A nested fraction means it's a keep, change, flip. So it's going to keep, so I'm going to keep the sine of x over cosine of x. I'm going to change the division into a multiplication, and I'm going to flip or take the reciprocal of this, and it's going to be sine of x over cosine of x. Okay, that's not looking great so far. Let's try it again. Okay, let's keep multiplying out everything. Wait, sine of x over 1. What am I saying here? I took the reciprocal and randomly put in another cosine by accident. Okay, so that is a reciprocal, that's a reciprocal. Okay, everything's good so far. Sine of x times sine of x. Okay, there's two of those, so it's sine squared of x. That's not going to go anywhere anytime soon. And then still cosine of x. Okay, well, that's a problem. I have everything in terms of cosine of x except for that sine squared. So is there some way of getting rid of a sine squared? And oh, you'll remember that advice that Mr. Sindel said from like 10 minutes ago, which said, hey, if you ever see a sine squared or a cosine squared, remember, if you add them together, they add up to 1, again, if you have like an x on the inside, if you have an x on the inside. So if I want to get rid of a sine squared, get this sine squared by itself and see what it's equal to. If I subtract a cosine squared of x on both sides, subtract a cosine squared of x on both sides, then those are gone, and you're left with this statement, this identity that says sine squared of x is still equal to 1 minus cosine squared of x, which means if this sine squared is this sine squared is also that 1 minus cosine squared. So I can say now the top is now 1 minus cosine squared of x. The denominator is just cosine of x. And we're done. That satisfies the puzzle. The puzzle said, hey, I want to write everything with just cosine of x. Well, I mean, I guess I have a 1. You're allowed to have numbers there. You just no other trig function. I can't have a sine or cotangent or anything like that. If you're only using cosine and other numbers, you're good to go, and I have satisfied the puzzle. So, ta-da. All right, so there are a few other formulas that'll be helpful, and we'll see why in a second. And they're just the sum and difference identities and double angle identities. And I can show where these come from. They're pretty fun. It's a cute little diagram. But for now, let's just memorize them. And we'll talk about, again, how to memorize a ton of stuff in very little time. So my recommendation on how to remember sine versus cosine when you're adding and subtracting angles. The first thing that students will notice is when I have a plus sign, the answer is a plus sign when I have a sine function. So S stands for same sign. When I have a plus, it stays a plus. But if you have a cosine, the plus changes into a minus sign. The C stands for change the sign. The other things that are interesting is that sine has two different functions and cosine has two of the same functions. And yeah, I'll go through those in a second, but try to have those memorized. We'll see where they go in a second. When I have sine of double of an angle, it turns into 2 sine times cosine. No other way to just, you guys have to remember that one. You might think that cosine of 2 theta has 3 different formulas, and you'd be right, but they all come from this one formula. So if you can remember this one formula, which looks really similar, right? If I did a plus sign right there, that would have been the Pythagorean identity, cosine squared plus sine squared. But I have a minus sign starting with a cosine, meaning it's a double identity. And these both come from the fact that you can rewrite cosine squared as 1 minus sine squared, and you can rewrite sine squared as 1 minus cosine squared from the Pythagorean identity. So you can rederive each of these here. Let me do one of them really quickly just to prove that I can. I happen to know that cosine squared of, we'll do theta in this case, plus sine squared of theta is equal to 1, because this is the Pythagorean identity that I memorized first. That should be the first thing that you memorize in this lesson. Let's just randomly say, hey, cosine squared. I'm going to say, okay, if you're cosine squared and you're cosine squared, let me move all of you to the right, and I now have cosine squared of theta is equal to 1 minus sine squared of theta, because I subtracted sine squared of theta on each side, which means this is now written as 1 minus sine squared of theta. And how many of these minus sine squareds of theta do I have? I have 2 of those sine squared of theta, and I saw that one right there. So you can rederive these, again, if you had solved for sine squared. In the second case, you would have gotten this second formula. So it is a bit confusing. There are 3 different ways of doing your cosine double angle formula, but there they are. Okay, so let's try to apply these to see where they come from, or what they'll be helpful for. So which of these are equivalent to this expression? Hard, but I'm noticing the general form. I'm kind of ignoring the angle here, and I see, oh, 2 sine times cosine. 2 sine times cosine. That looks like that. And it is that. So, and it's the same angle, which means in order to move from here to here, I need to just have that angle and double it. So recognizing the form of these is really important. So really all it's asking us to do is double the angle. So I have the angle of pi over 14. If I double that, then I have a 2 here. And hey, the 2 and the 14 will cross cancel and make a pi over 7. So this is going to be pi over 7. And is this the double angle formula for a cosine or for a sine? It's for a sine, so I can immediately cross off the cosine, and that one has a cosine in it as well. So which of these is it? Well, pi over 7, the correct answer here is obviously C. All right. Example 5, let's try this one. So which of the following are an equivalent form of 4 cosine of 2x? Okay, well, the first thing I see is, oh, it's a double angle formula because there's 2 times something happening in here. And I remember, this is the one that has 3 different formulas. I only have one of them memorized, which is this one. Cosine of 2x is equal to cosine squared of x minus sine squared of x. And we cross our fingers and hope that's the one that they chose. And I'm looking at the multiple choice answers, and that one was close. It was really close, but they did a plus sign, and it has to be a minus sign. So that one was probably the red herring. I'm pretty sure that one's not going to be the case, but I'm not 100%, so I can't cross it off. Okay, well, let's just use another one then. So if it wasn't the first one, maybe it's this one. Maybe it's 1 minus 2 sine squared. And 1 minus 2, I don't see this one, because if we had a minus 2 sine squared, you would see like a minus sine squared, minus sine squared, minus sine squared. None of those, so it's not that one. It has to be the last one then, 2 cosine squared minus 1. So 2 cosine squared minus 1, 2 cosine, oh, okay, so 2 cosine squared, but then the minus is on the wrong spot. It should have been minus 4. So 2 cosine, okay, so there's the answer. So it's C. So check this one out. Look how similar these look. 2 cosine squared minus 1, something that's doubled cosine squared minus the original 1. So if I had taken this 4 right here and distributed it into that 2 and to that 1, I would have gotten an 8 and a minus 4. That's where that came from. Excellent. So this is, again, memorizing those formulas is super duper important. Example 6, which of the following expressions is equal to this. Okay, so the first thing that I'm noticing is that there's a ton of trig. There's 4 trig expressions, which means it's an angle addition or subtraction. It's one of these two, right? It's one of those or one of those. So how do you tell the difference between them? If it's a double cosine, it's cosine. If it's sine and cosine mixed together, it's a sine. So let's come back down here. Okay, it's double cosine. So okay, this one is going to be cosine of something. So I'm looking for cosine or cosine. It's not going to be sine of anything. It's not going to be sine of anything. And how do I decide between pi over 16 and 3 pi over 16? Well, you have to ask yourself, are these two angles being added or are they being subtracted? I happen to know that because we're choosing cosine, the C for cosine stands for change, which means if this was a minus sign, it was actually trying to add the angles. What we were trying to do here is do cosine of things added together. Well, what two things added together? That angle and that angle. So I'm going to have pi over 8. Haha, silly Mr. Sindel. Pi over 8, and I need to add that with pi over 16. You just need like denominators there, so that means I'm going to multiply u by 2, multiply u by 2, and this is really going to be 2 pi over 16 plus 1 pi over 16, and that's just 3 pi over 16 on the insides. 3 pi over 16 for the argument means we have option C for number 6. All right, and then we move on to our last page. Oh boy. Okay, so we have point P and has points 5, 12, and oh, that means our radius is 13. We're not dealing with a unit circle. Be careful, everyone. The coordinates, what are the value? Okay, so sine of 2 theta. So I happen to have that one memorized now that I've played enough on Blue-Kit. And that's the way that I've been memorizing these. And I highly suggest that to you guys as well, unless you have some other form of flashcards. I've already made flashcards for this lesson, so I highly recommend you just use mine. Sine of 2 theta is the same thing as 2 sine of that original theta before doubling times cosine of that same angle. If you don't have that one memorized, go memorize it. So from here, I just need to find what is sine of theta, what is cosine of theta, and plug it in. So let's come up here. What is sine of theta? What is cosine of theta? If I have those, I'm basically done. Well, sine of theta normally is just the y-coordinate if this was a unit circle. The fact that it's not a unit circle means we have to say, okay, it's the y-coordinate 12 divided by the radius. The radius used to be 1, so we used to say just divide by 1, but now I have to say divide by 13. Cosine, equivalently, is the x-coordinate divided by the radius. It is 5 divided by 13. So plugging both of those values in means we have 2 times, it's going to be 12 over 13 times cosine, which is 5 over 13. What do we get? 2 times 5 is 10. 10 times 12 means it's 12 with a 0. And then on the bottom, 13 times 13 is 169. And 13 is a prime number, which means the factors of 169 are only 13 and 13. And since there are no 13s in the numerator, I cannot reduce this fraction. These two numbers are co-prime, and we have our final answer. All right, let's try another one. Oh boy. Okay, so these ones are like the really traditional examples where you need to have these formulas memorized. It's super, super useful because we don't know what this angle is. We just happen to know that it's at this one spot. We need to find what is cosine, what is the x position when I double that angle. When I double that angle, it's going to come down and live like maybe down there. I don't know exactly where it is, and that's the whole point. All I know is I can use trig identities to solve for this. So let's do that. Cosine of 2 theta. We could use a bunch of different formulas to solve for this one, which is kind of cool. I'm just going to use, does it matter which one? I kind of only want to use one trig function because remember that there's 3 functions I can use. I could use the first one, the second one, or the third one. I don't know. I'm kind of leaning towards the third one because there's no minus a big chunk of thing. It's a big chunk minus 1. I kind of prefer that one, but it doesn't matter. Here, let me just choose the first one that I have memorized. I have that one memorized. I might as well use it, right? So check it out. I'm going to say this is equal to, in pen, this is going to be equal to cosine squared theta minus sine squared, and it's not theta, it's alpha, right? So I'll switch this to an alpha. The way that I write my alphas is it's a little fish of a little fish. That was a terrible fish, but whatever. Okay, so what is that? I need to find what sine and cosine are of, okay, so notice that these are both different problems. That's beta over here. So I'm only talking about alpha over here. So I can say cosine of alpha, a little fish, is going to be equal to, well, it's the x-coordinate divided by the radius. So x-coordinate divided by the radius is -5 divided by 6, and then sine of my little fishy alpha is going to be equal to the square root of 11 over 6. So plugging both of those in, Cosine squared is negative 5 over 6. So negative 5 over 6, and then I need to square that and then subtract. Sine squared is going to be the square root of 11 over 6, and that whole thing needs to be squared as well. All right, so what is that? Well, whenever I square something that's positive, so this is going to be 25 over 36, and then I need to subtract. The square and square root here will cancel each other out, so it's 11, but I still need to distribute the square to the bottom as well, and it's going to be over 36, and 25 minus 11 is 14, right? 14 over 36. So I'll say this is equal to 14 over 36. Oh wait, these are both divisible by 2, so I can say divide the top and bottom by 2. It's going to be 7 over 18. Cool. Let's call that one. And by the way, if you had used any of the other two formulas, like maybe use 2 cosine squared of theta minus 1, you would have still gotten the same answer. All of them work. Let's try another one. Okay, an angle addition for sine. So I happen to remember using Blukit that this one is going to be equal to S for same sign. So there's going to be the same plus sign in between, and it mixes the sine and the cosine. So if it mixes the sine and the cosine, I'm just going to say sine of alpha, little fishy, times cosine of the other angle. We'll call that one beta, just has a bigger tail. Let's move the plus sign out of the way. Plus sign out of the way. There we go. And then I'm going to take cosine of alpha, little fishy, times sine of beta. There you go. So again, the question is, what are each of these? And over here, I need to figure out what sine of beta and cosine of beta are. So let's say cosine of beta is going to be the x-coordinate divided by the radius. So it's going to be 2 divided by 3. And then sine of beta is going to be the y-coordinate, the square root of 5, divided by the radius, 3. All right, so I can plug all of that in. So sine of alpha is square root of 11 over 6. So this is the square root of 11 over 6 times cosine of beta. Cosine of beta is 2/3. 2/3 plus. Okay, cosine of alpha. Cosine of alpha is negative 5/6. Negative 5/6 times sine of beta. Sine of beta is square root of 5 over 3. Square root of 5 over 3. Luckily, I'm looking at the denominators ahead of time. They're both the same denominator, so I don't have to do anything tricky. I'm going to have 2 root 11 over 18 plus negative 5 root 5 over 18. And you put those into one giant fraction and call it a day. 2 root 11 minus 5 root 5 all over 18. Done and done. And I can move all of you and put you right there and box it. I just want enough room for my box. Ta-da. All right, let's try another one. Ooh, angle subtraction. Okay, so I happen to have this one memorized as well. So the way that this one works, if I do cosine of alpha minus beta, that's the same thing as saying, I believe it starts with cosine first. I'm trying to remember. Yeah, it's going to be the double cosine, right? So it's going to be cosine of alpha, cosine of beta, and then C stands for change, so change the subtraction into, whoa, addition. Come on, where are we? Done here. So it's going to be addition, and then you do the other two. So it's going to be sine of alpha, sine of beta, and we ran out of room. All right, so I need to use all of that. So again, I just need to plug it in. What is cosine of alpha? Zooming out. Cosine of alpha is negative 5/6, so you are negative 5/6. Negative 5/6 times cosine of beta. Cosine of beta is 2/3. Come down here and say this is 2/3 plus, okay, sine of alpha. Sine of alpha is square root of 11 over 6. So we come down here and say this is the square root of 11 over 6 times, and then sine of beta. Sine of beta is square root of 5 over 3. So we come down here, it is the square root of 5 over 3. And they should always have the same denominator when we're mixing them in this way, just based on the formulas. And I'm seeing that the numerator is going to be negative 10 and then over 18 plus, and this is going to be root 55 over 18, and then combine them into one happy fraction family. And then you can say this is root 55 minus 10 all over 18 and call it a day. Whew. That was it for the notes for topic 3.12. Let's check out all the different pages that we had and finally talk about how I would study for this. So over here, I have a topic 3.12 blue kit for equivalent representations. You can see if I come in here and I edit it, you can see all the different questions if I show the answers. It has all the different formulas from this lesson that you're supposed to have memorized, both the left side and the right side, with what I think are the common mistakes. So if you want to play this thing, you would play it by, here, let me go back, scrolling down to the bottom where I just made this thing. Right here. I'm going to do a solo version of this, and I can choose between playing game modes like Monster Brawl, Tower Defense. Honestly, Tower Defense 2 is my all-time favorite, but sometimes I'm just not in the mood to game. I just want to study. So you come down here to the study tool and you can hit play, and you just do these. You say, oh yeah, cosine squared plus sine squared is 1. So this one is the green one down here in the bottom left. Hey, I got it. And then, okay, I'm seeing, it's mixing things, so it's going to be sine of something, and sine stands for same sign, so it's going to be sine of the same minus, so it should be sine of a minus b, should be the bottom left again. I got it, hooray. And you keep doing these over and over until you eventually get it. This one should be mixing them with a plus sign, mixing them with a plus sign as blue, and you keep going. And this will go on endlessly until you get it. I'm gonna hit the checker flag in the top right, so I go ahead and call it a day, and you get some rewards that are kind of trivial, but it's still kind of fun. That's how I would study. Go use it, it's for free, guys, and have a nice day. Bye.